Liquid Chemical can provide mixing, sampling, and testing services for fiber-reinforced concrete at their testing laboratories in Cleveland, Ohio. ASTM test methods such as C1609 for beams and C1550 for round panels, along with other European standards for measuring the performance of FRC, are conducted under controlled environments and can be set to evaluate the performance of FRC under different conditions and with varying concrete mixture designs. Not all fibers have the same manufactured physical and material properties. Proper mixing and casting procedures for fiber can have a significant impact on FRC in the field. It is very important to maintain consistency and ensure fibers are properly distributed in concrete prior to running these standardized tests. ASTM C1609 is a test conducted on large flexural beams that measure the post-crack load carrying capacity of concrete. This test must be conducted on a closed-loop servo-controlled machine that uses the deflection of the beam to control the load and speed of the test. These tests then evaluate how fibers perform in concrete. The data that is generated can be used by design methods such as the recently published American Concrete Institute document ACI 544.4R. This document helps to determine how much fiber is necessary to be placed in concrete to meet specific engineering requirements. The EN 14651 test is a European version of the C1609 method, but with slight variations in the procedure and setup of the beams. ASTM C1550 is a test conducted on large panels and typically used in the shotcrete and underground industry. This test must also be performed under controlled mixing and placing conditions and tested using similar equipment. All of these test methods are designed to measure how fibers can provide residual strength to concrete or give engineering data on the capacity of concrete to maintain integrity and hold together even after concrete is cracked. Fiber manufacturers should always be ready to supply testing results with each design project to meet specification and engineering requirements. With these test results, designers can provide correct fiber dosages in comparison to distributed steel reinforcement, such as rebar or wire mesh, into many successful applications of FRC. Projects with fiber-reinforced concrete should always contain proper specifications and drawing notes with engineered data coming from approved test methods. This level of detail will ensure proper placement and performance of FRC in the field. For more information on these tests, learning about proper consolidation methods and many applications using fiber-reinforced concrete, or to have your next FRC project evaluated by Euclid Chemical, visit our website or contact one of our local sales representatives today.
Welcome you all for this lab session of flexural toughness characterization of fiber-reinforced concrete. I am Sujata Jose, doctoral research scholar working in the area of fiber-reinforced concrete in Building Technology and Construction Management Division in IIT Madras. So first of all, the main disadvantage of using plain concrete is its brittle failure. So the advantage of fiber-reinforced concrete over plain concrete is its enhanced ductility, post-crack load carrying capacity, etc. So this post-crack load carrying capacity is captured by the post-peak response, which can be derived from this test of flexural toughness characterization. Objective of this test is to measure the effectiveness of fibers and to obtain a post-peak response. So this is a specimen of fiber-reinforced concrete. So there are different types of fibers in the market, like steel, polymer, which is used for many applications like flooring, pavements, slabs on grade, tunnel linings, etc. So these are some steel fibers, and recently new materials are being introduced in the market, and this is an amorphous metallic fiber. All these different types of fibers are used for different applications. So now, regarding the characterization of fiber reinforced concrete, there are two typical tests, notched and unnotched beam test. So this is a specimen cast on fiber reinforced concrete. So this testing is based on an EN 14651 and Rylem TC 162. So in this notch test, we are actually cutting a notch in the mid width of the test specimen. Why do we need to cut the notches? We are forcing a weak plane in that area so that a crack happens in that area. So this is the specimen, and the notch is cut using saw cutter, and wet sawing is done, and again curing is done for another 3 days to avoid any thermal cracks. So now the typical depth and width of a notch is 25 mm and 3 mm, and the specimen dimensions are 150 by 150 by 700, and the span is 500 mm. So now, as I told you before, this is a closed loop testing system, which is a displacement control test. Closed loop testing system works on a feedback system, unlike an open loop, which is only an input and an output. So now this is a displacement control test in order to get the post peak response. So here the displacement parameter is crack opening, which is controlled with the clip gauge. So this is the clip gauge through which we control the test. This clip gauge is fixed onto the specimen on a knife edge, which is fixed on either side of the notch at the midspan. But along with crack opening, we are even measuring deflection. So deflection is measured by two LVDTs, which is mounted on either side of the specimen using this frame, and this frame is fixed onto the specimen by means of a C-shaped collar. So although we are measuring deflection and crack opening, the control parameter, as this is a displacement control test, the control parameter is clip gauge, CMOD, which is measured by the clip gauge. So now this test is continued until a crack opening of 4 mm. One more important thing to be noticed is that the notch is cut at the mid width in the direction which is perpendicular to the casting face. So this is the casting face of the specimen, and the notch is cut in a direction which is perpendicular to the casting surface, and the loading direction is also perpendicular to the casting face. So loading on top, notch on the bottom, and casting will be perpendicular to it. So now let's move on to see how we are going to mount the specimen onto the testing frame. So this is the setup in which we have mounted our fiber reinforced concrete specimen onto the testing system. So this is a controls closed loop testing system, and we have mounted here 3 sensors as I have explained before. That is the clip gauge in which we control the test, that is here, and LVDTs which is fixed on either side of the specimen onto the rigid frame which is fixed to the specimen by means of a C-shaped collar, and the deflection of the specimen we consider by taking an average of the LVDT readings of the 2 LVDTs on either side, but the control is done with the clip gauge CMOD which is mounted onto the knife edge at the mid width. These sensors are connected to the data acquisition system through which we acquire data through our advanced interface. Now let's move on to see how we do the testing. So initially we will start the test with load control till about around 40% of the peak load is reached, and then we will shift on to the CMOD or crack mouth opening displacement control. Now let's move on to the test. Now the test is running. The peak load is achieved in 2 to 3 minutes time, and the complete duration of the test, that is for a CMOD or a crack mouth opening of around 4 mm, it takes to around 45 minutes for steel fiber reinforced concrete. Now the test is completed. As you can see that although there is a crack which is developed, there was no brittle or a catastrophic failure. That's because of the presence of fiber reinforced concrete. But at the same time we have got the post peak response, that is the performance of fibers after peak. So what is the load carrying capacity at different crack openings we can be able to derive from this test. So now our test is complete. We got 2 responses, the load crack opening response and load deflection response. So from these responses we derive the flexural toughness parameters. From the load crack opening response we calculate the residual flexural strength, which is the flexural strength at different crack openings of 0.5, 1.5, 2.5 and 3.5 mm. Whereas from the load deflection response we calculate the equivalent flexural strength, which is based on the average load at different deflection limits. So these parameters are used in the design of FRC elements. Now this is a typical load crack opening response of plain concrete and fiber reinforced concrete. As you can see in the case of plain concrete, there is a sudden drop after the peak which shows a brittle failure. Whereas in the case of fiber reinforced concrete, there is an enhanced post peak load carrying capacity which is due to the stress transfer by the fibers across the crack, which was captured in our test that we shown now. So this testing of characterization of fiber reinforced concrete was done using the closed loop testing system with displacement control, and thank you for watching.
Concrete is naturally brittle. Typical stresses like impact, fatigue, and loading lead to cracking and eventual failure. Adding reinforcement to the concrete helps to absorb these stresses and to limit the formation of cracks, increasing the load-bearing capacity and ductility of the concrete structure. There are several ways of reinforcing concrete. We've all heard about rebar and steel mesh, but did you know steel fiber is just as strong and reliable? Since its introduction over 40 years ago, steel fiber reinforcement has proven its merits in the most demanding structures and applications. The core difference between steel fiber and other reinforcement solutions is that fibers are part of the concrete matrix, turning it into a composite material. Instead of providing strength in distinct locations, steel fibers form a reinforcing network throughout the entire concrete structure, increasing its overall ductility. So how does this translate into concrete behavior? Take a random concrete structure. When subjected to loading, compressive and tension stresses start to build. Over time, small cracks will appear in places where the stress reaches a critical point. Steel fiber interacts within the concrete matrix, absorbing tensile stresses at any point and in any direction. As a result, steel fiber picks up small cracks much faster than traditional reinforcement. When a crack occurs, the hooked ends of the fibers remain solidly anchored on each side of the crack, acting as a stress transfer media. Once the maximum bond strength with the concrete is reached, the pull-out takes full effect. This enables the next fiber to take over, delaying cracks from growing. Different loads require different steel fibers. To meet any design requirement, Beckart offers 3 steel fiber types: Dramix 3D, 4D, and 5D. Each fiber has a different hook, strength, and ductility. Consequently, they also behave slightly differently when dealing with stresses. Let's take a closer look. First up is Dramix 3D. When a small crack occurs, the 3D hooks firmly anchor inside the concrete matrix. As the stress increases, the hook slowly deforms. As soon as the fiber loses its bond with the concrete, the pull-out takes full effect. Dramix 4D provides the same process, but with even better anchorage and a significantly higher tensile strength of 1,650 Newton square millimeters or more. Dramix 5D behaves differently altogether. Here, the hooks never pull out from the concrete. As the stress increases, the wire slowly elongates until it reaches its maximum strength. With a tensile strength of 2,300 Newton square millimeters and elongation of 6%, concrete structures reinforced with 5D can take high flexural stresses over a long period. Based on these behaviors, we can conclude that Dramix steel fibers effectively increase the load-bearing capacity of concrete. It can be used in almost any concrete structure with or without additional reinforcement, where the ductility of your concrete structure depends on the length-diameter ratio of the fibers and the number of fibers used per cubic meter. It is essential that enough fibers overlap to create a continuous network in the concrete mix. Do you need help finding the right fiber and determining the right dosage? Beckart gladly provides expert guidance through each step of your project from design to execution. Visit www.beckart.com/Dramix to get in touch.
What's up, everybody? This is Harry, and I want to go over some different cement concrete reinforcing options that are available out there. So, in case you don't know, cement concrete has great compression strength. If you push down on concrete, it's very strong. But if you try and bend it, it'll break. It'll snap because it has no tensile strength. So normally in a cement job, concrete, you maybe have a slab that's 4 inches thick, and you'll have a rebar right in the center of that slab, and the rebars will be tied together, and they'll have like a checker pattern. So that's the rebar here. Now another option that's really good is this here. This is basalt rebar. This is rebar made from lava rock, and the good thing about this is it won't rust. It's much lighter than steel, and it's stronger than steel. And another great benefit is this stuff will come on a roll, so you can get a roll of it 300 feet long, and you can cut it to your own length, whatever length you require on the job. So that's a pretty nice thing. Also, if you're building around the coastal areas where there's salt air, the salt will rust the steel, and eventually that will break down the cement and make your cement weak. If you have this basalt rebar in there, you won't get that problem because there's no rusting with rock. Also, this is great for any areas where there's chemicals and things. This is immune to chemicals as well. So some other basalt items I wanted to show are these meshes here. So this is a sample pack that I ordered from this company, and here you can see the different patterns that they have. So this is the name in this pattern, and they have all these different patterns. You can see from my hand how big these are. Here's another, and they feel pretty stiff, especially the larger ones. I think they're made with like a resin. I'm not sure exactly how they're made, but it's really strong. There's some other patterns they have. So they have all different kinds of mats. You can see the names on some of these. There's another weave they have. So there are all kinds here. I suggest if you're planning on using any of this stuff, you order yourself a sample pack and see for yourself which one's going to work best for your project. Now this is another great option they have here, is this 3-ply rope. It's basalt rope, and this rope is used in a lot of dome projects, where domes similar to this dome that I'm building here will have one layer of cement put on, then they'll wrap around in a pattern with the 3-ply basalt rope. Then they'll spray or apply another layer of cement on top of that, and that way they're getting their tensile strength from the rope. So that's another great product. Here you have different lengths of basalt fiber chop. So if you look here, you can see the length of the fiber chop, and so they come different lengths. This one's a 18 millimeter. Here's a 50 millimeter. You can kind of see the lengths there. So it's all fiber chop. I ordered this pack, this sample pack first, before I decided to get the 50-pound bag of basalt fiber chop. So this is what I've been using in my dome project. I've been mixing up my cement and putting in like a big handful of this stuff in there. Into here. So that's the dome project. So this, all the cement you see here has the basalt fiber chop mixed into it. Now lastly, a great product here is this Helix micro rebar. The Helix micro rebar was designed to replace regular rebar. Ain't that something? So anyway, it's not a single little strand, but it's in these bunches here. So what you do is you take this Helix micro rebar and you throw it into your cement mix and you let it mix up, and then you can just pour into any form you're looking to make, whether it's a slab or you're doing some walls or whatever it is. And what'll happen is this stuff was actually designed to make bomb-proof structures. So it's really strong. So instead of having one rebar inside, for example, you have a 4-inch slab of concrete and you'll have a rebar right in the center of that. This here will be in every which way direction from top to bottom. So you're not going to have just one rebar in the center, but you'll have thousands of these going in every direction just like that in the cement, and that gives it so much more strength than regular rebar. So on their website they actually show a video of them doing a test where they have a regular slab of cement with rebar in it, and they put 10 pounds of C4 explosives on it, and it blows a giant hole in the concrete, and you see all the rebars all bent and everything. They do the same test with a slab of concrete with this micro rebar in it. The bomb goes off, and the cement barely is even cracked. There's barely a crack that shows up. That's how much powerful this is in comparison. So I said, all right, I want to build my house out of that. So one test that I'm doing currently is I made aircrete. I'd never seen anyone do any tests with aircrete with helix micro rebar in it. So I poured some aircrete in this box. I have regular aircrete with no reinforcing fibers in it, and I have the same aircrete with this helix micro rebar in here. And I just want to compare the two and see how well this micro rebar works with aircrete. I know already it works with regular concrete. What I'm curious as to how well it'll work with the aircrete. So that's a test that I'm doing. But otherwise, that's it for now. I just wanted to show everyone the different products that are available for adding into your cement work to give you your tensile strength. There's more than just the iron rebar available. Like I said, these basalt rebars are really good stuff. So I'd highly recommend this, especially in salt air areas. Anyway, that's it for now. This is Harry, and I'll catch you guys later. Peace out.